3.2, using vectors on a motion diagram. So I've shown a motion diagram here that depicts an object that starts out kind of slow and is getting faster. Therefore, this object is accelerating. And I'd like to show you how you can use this vector addition and subtraction idea to get a sense for what the acceleration of an object looks like. Now, we already know this object is accelerating because we've studied this before. And in fact, you probably can realize the object should be accelerating to the right. The object's moving to the right, it's getting faster, so the acceleration should be the same direction as the velocity, which would be to the right. Now, I want to prove this to you using vectors. Keep in mind over here that we have the definition of average acceleration. Average acceleration is equal to the change in velocity divided by the change in time. Change in velocity is a vector quantity. It's the difference or subtraction of two vectors. So this has a direction. The average acceleration also has a direction, and the equal sign here, and these two things being the only things with directions, says that the acceleration must have the same direction as the change in velocity. They're not the same, they're not the same number, but they have to have the same direction. So by finding the change in velocity between two times, we should get a sense for which direction the acceleration is pointing. And that's what we're going to do. Over here I have the motion diagram depicted at time 1 and time 2, and I'm going to find the change in velocity from time 1 to time 2. And that will tell me what the average acceleration is, or at least the direction of the average acceleration during that time interval. So delta v in this case is v final minus v initial, so that v final would be the velocity at time 2 minus v initial, the velocity at time 1. Now remember from the previous recording that minus v initial is the same thing as v initial, but pointing the opposite direction. So I've tip-to-tailed that over here in this picture. We have v final, the same vector that we had here, and we've tip-to-tailed to it negative v initial. Here's v initial, so minus vi is this vector pointing to the left. And I didn't tip-to-tail it so that they're connected because the lines are parallel. If I do draw it so that the tips and tails are connected, these arrows are going to be on top of one another and kind of difficult to see. So I've placed it just above. And you can see that when I add these two arrows tip to tail, the beginning of the chain is over here. The end of the chain is over here. So this red arrow is the resultant. This red arrow is the change in velocity. This red arrow points to the right. So from time 1 to time 2, the change in velocity is to the right. And since the change in velocity has the same direction as the acceleration must point to the right as well. And I drew that motion diagram again on the bottom of the screen, and this time with acceleration arrows. From time 0 to time 1, the velocity, the average velocity, looks like this. The object has an acceleration to the right. The acceleration is like instructions on how the velocity should change. This is saying the velocity in the next second should point more to the right. And it does. At time 1, the velocity arrow is longer. It should continue to accelerate and point more to the right. And at time 2, again it's longer, and so on and so forth. Here is a novel motion, one that we have not yet studied. It's the motion of an object traveling along a circle. And in this case, these velocities are instantaneous velocities as the object travels around the circle and does so at a constant speed. So this is the motion of an object in circular motion at a constant speed. It's called uniform circular motion when these two things are true. Each one of these velocity vectors is tangent to the path that the object is traveling along the circle. Although the object has a constant speed, it does not have a constant velocity, because at each instant, the velocity vector being tangent to the circle is changing direction. Remember that velocity has a direction and a magnitude. So if velocity has a direction and a magnitude, then a change in velocity can result from either one of these things changing. The velocity could just change magnitude, which is what we've seen so far. That would be like an object getting faster and slower. But the velocity could change direction, and only change direction, and still constitute a changing velocity. And that's what we're seeing up here. Every one of these arrows is the same length, but they're each pointing in different directions. So this is also an acceleration. It's completely possible for an object traveling at a constant speed to accelerate. An object that is not getting faster or slower can be accelerating, provided it's changing direction. So how do we calculate the acceleration for something like this? Typically, when we've calculated accelerations before, we've dealt with a case where the speed was changing, and we would put those numbers into the equation for delta v over delta t, and we would churn out an acceleration. But the speeds aren't changing here. If all of these are 5 meters per second, how do we plug those numbers into delta v over delta t to get our acceleration? Well, we're not going to answer that yet, but we are going to get a sense for what direction the acceleration points. And the way that we're going to do that is by doing the same thing that we did in this previous slide. We're going to find delta v. We're going to take 2 times, find the difference in the velocity vectors using the tip-to-tail method, and see which direction delta v points. We should get something, because we know the object should be accelerating, even though it's not getting faster or slower. So what we did here is delta v from time 1 to time 3. So here is our v initial, velocity at time 1 second, and our v final will be the velocity at time 3. Here is our v final. And then delta v from time 1 to 3 will be the velocity at time 3 minus the velocity at time 1. So again, we'll need to do our trick where we take the object, take the velocity 1, the one that's being subtracted, and take this vector and flip its direction. If v1 pointing straight up looks like this, then minus v1 is the same length but pointing straight down. I did that tip-to-tail diagram over here. I took v3, which looks like this, and I redrew it over here. Then I added to that, using the tip-to-tail method, minus v1, an arrow pointing straight downward, but the same length as v1. The resultant, which will be delta v, points from the beginning of this chain to the end of the chain. So it points down and to the right, and I drew it with this large blue vector here. I redrew it one more time here so that I could move it around. If this is delta v from time 1 to time 3, then I'm going to place it at the time in between time 1 and time 3, which is time 2. If I place it at time 2, you're getting a sense for the instantaneous change in velocity at this instant, at 2 seconds. It's the average from 1 to 3, but it's the instantaneous value at time 2. And if you see where it points to a rather special spot. It points right towards the center of the circle. This gives us some sort of indication that, yes, this object is accelerating, and the direction is pretty special. If an object is traveling in a circular motion, in uniform circular motion, then its acceleration at any instant in time should point right towards the center of the circular motion. And that's something that we're going to expand upon as we go forward in the course.